The directions say to solve the given differential equation by using an appropriate substitution. Let's take a look at example 1. Suppose we are given dy dx is equal to x plus y plus 1 quantity squared. So what we're going to do is we're going to let u equal x plus y plus 1. Du dx is equal to 1 plus dy dx. So solving for dy dx, we get dy dx is equal to du dx minus 1. But recall, dy dx is x plus y plus 1 all raised to the second power. So if we make our substitution, we get du dx minus 1 is equal to u squared. Solving for du dx, we get du dx is 1 plus u squared. Now, this substitution turned this differential equation into essentially a separable differential equation. So we can rewrite this as follows. We can say 1 over 1 plus u squared du is equal to dx. And now we can integrate both sides. So the integral of 1 over 1 plus u squared du is equal to the integral of dx, right here. So arctangent of u is equal to x plus c. Solving for u, we get u equals tangent of x plus c. But remember that u is x plus y plus 1. So making our substitution, we get x plus y plus 1 is equal to tangent of x plus c. Solving for y, we get y equals negative x minus 1 plus the tangent of x plus c. Example 2. Suppose we're given dy dx is equal to tangent squared of x plus y. So we're going to let u equal x plus y. Du dx is 1 plus dy dx. Solving for dy dx, we get dy dx is du dx minus 1. Now, remember that dy dx is tangent squared of x plus y. And if we make our substitution, we get du dx minus 1 is tangent squared of u. Solving for du dx, we get du dx is 1 plus tangent squared of u. But 1 plus tangent squared of u is secant squared of u. So du dx is equal to secant squared of u. And just like that, we have another separable differential equation. So we can write this as follows. We can say 1 over secant squared of u du is equal to dx. But 1 over secant squared of u is cosine squared of u. So cosine squared of u du is equal to dx. And we get to integrate both sides. So the integral of cosine squared of u du is equal to the integral of dx. But we can write cosine squared of u, so let's go back. Remember that cosine squared of u is 1/2 of 1 plus cosine of 2u. So this integral can be written as follows. We can get 1/2 the integral of 1 plus cosine of 2u du is equal to the integral of dx. So 1/2 the quantity of u plus 1/2 sine of 2u is equal to x plus c, right here. So distributing the 1/2 inside, we get 1/2 u plus 1/4 sine of 2u is equal to x plus c. Now I get to replace u with x plus y. So 1/2 of x plus y plus 1/4 sine of 2x plus 2y is equal to x plus c. And this is where you want to talk to your instructor to see how far your instructor wants you to simplify. So I'm going to leave it in this form. And with that, let's talk about example 3. Suppose dy dx is 2 plus the square root of y minus 2x plus 3. I'm going to let u equal y minus 2x plus 3. Du dx is equal to dy dx minus 2. Solving for dy dx, we get dy dx is equal to du dx plus 2, right here. And just like before, remember that dy dx is 2 plus the square root of y minus 2x plus 3. Making my substitution, I get du dx plus 2 is equal to 2 plus the square root of u, right here. The 2's cancel, and we get du dx is equal to the square root of u. And just like that, we have another separable differential equation. And so 1 over the square root of u du is equal to dx. Integrate both sides. So the integral of 1 over the square root of u du is equal to the integral of dx. So 2 square root of u is x plus c. Square both sides. So 4u is x plus c to the second. Solve for u, and we get u equals 1/4 of x plus c to the second. And then I'm going to replace u. Remember, u is y minus 2x plus 3. So y minus 2x plus 3 is 1/4 of x plus c to the second. And this is a perfect problem to solve for y. And so I'm going to add 2x, subtract 3 to both sides. I'm going to add 2x, subtract 3. And when I do, I get y equals 2x minus 3 plus 1/4 of x plus c raised to the second. Example 4. Suppose I have dy dx is equal to cosine of x plus y, and we have an initial condition where y of 0 is pi over 4. And just like in the first 3 examples, I'm going to let u equal x plus y. Du dx is 1 plus dy dx. And I want to isolate that dy dx. And when I do, I get dy dx is equal to du dx minus 1. And so remember that dy dx is cosine of x plus y. Making my substitution, I get du dx minus 1 is cosine of u. And then adding 1 to both sides, I get du dx is 1 plus cosine of u, right? Again, another separable differential equation. So 1 over 1 plus cosine of u du is equal to dx. And so I need to work with 1 over 1 plus cosine of u. And so I'm going to multiply the numerator and denominator on the left side by 1 minus cosine of u. So 1 minus cosine of u over 1 plus cosine u times 1 minus cosine u du is equal to dx, which says 1 minus cosine u over 1 minus cosine squared of u du is equal to dx. But remember, 1 minus cosine squared u is equal to sine squared of u. So 1 minus cosine of u over sine squared u du is equal to dx. And I'm going to split up the fraction. And so 1 over sine squared u minus cosine of u over sine squared u, that quantity du is equal to dx, which says cosecant squared u minus cotangent u cosecant u du is equal to dx. After all that work, we get to integrate both sides. So the integral of cosecant squared of u minus cotangent u cosecant u du is equal to the integral of dx. So negative cotangent of u plus cosecant of u is equal to x plus c. But remember that u is x plus y. So negative cotangent of x plus y plus cosecant of x plus y is equal to x plus c. But we have an initial condition after all that work. We know that y of 0 is equal to pi over 4. And what that means is when x is 0, y has to be pi over 4. And this initial condition will allow us to solve for c. And so negative cotangent of pi over 4 plus cosecant of pi over 4 is equal to c. Solving for c, we get c equals negative 1 plus the square root of 2. So negative cotangent of x plus y plus cosecant of x plus y is equal to x minus 1 plus the square root of 2. And that will do it for this video where we solved differential equations by an appropriate substitution. And these are first order differential equations. Okay, thank you.